try to do the exercise in the upper triangle. So what is the result of the upper triangle? Did you try? No. Did you have time? Okay. So let me do just one remark. So remark, just the only remark I think of the course on systems. So let say M on M. So measure equal to 2. And consider a matrix so suppose that we have a real matrix with the following property. A say lambda 1, lambda 2, lambda. Okay. We want to consider ut plus a ux equals 0, say u into c1 r1 plus 1 with values in Rn. So now utx is a vector, okay? So u of tx is a vector. And say u times 0 u0 of x, say u0 of c1. So why this? Yesterday we saw that try to rewrite it. So if you take n equal to 2, so call u equal u2, u. So you can write ut equal dx, dt equal ux. Then maybe there is some c missing here, so maybe 1 over c. So what happens if I do utt here, vxt, 1 over c squared, so this implies 1 over c squared utt equal vxt equal uxx. No? So let us normalize for 1 minute, just for this discussion. Let us normalize with c equal 1, okay? Just for this, for the moment, okay? Just let's normalize c equal 1. So utt equal vx. So if we call u, so if we we can write this with capital A instead. So, and if I call capital U equal UV, so this should be more precise than maybe capital U, but it's clear the notation of what I'm using. So UT is equal to UT dP, UX is equal to UX dx. So if I do A UT, AU, let me see, AUX, what is this? It is 0, -1, -1, 0, UX dx. So it is equal to minus Px and minus Ux. So I can write UT plus UX. No? This is equivalent to probably if we insert C here, probably the matrix with the constant C should be let's see, UT equals CVX, VT equals CUX. So what do we get? UTT equals CVXT equal C squared, yes. Okay, so maybe we can reinsert the constant C and put C here, okay? C here. Okay, it's correct. Does it work? Seems it works, no? 1 over C squared. No? Because if from here you get UTT equals CVXT, which is C squared UXX. So this is actually even here there is some symmetry. In this case, A is symmetric, 2 by 2 symmetric. The eigenvalues of capital A, so the determinant of A minus lambda identity, it is what? So it is the determinant of minus lambda minus C minus. So we have two eigenvalues, lambda 1 minus. So we are exactly in this case here, okay? Situation changes, of course, if you change one sign here. If you change one sign here, the situation is completely different. Okay? So that sign is very important. So in some sense, we are very close to the wave equation. So what can we do here? So this is a real matrix with n distinct eigenvalues. So there is a basis. So we can find a basis over n consisting of eigenvectors. Okay. I can call it a basis, so R1, Rn, eigenvectors. Possibly normalizing. We can suppose okay. Now it is convenient also now to consider the dual basis. So this sum, okay. So A over I is equal to lambda I. Okay. Okay. Now it is convenient also to consider a dual basis. We know the dual basis exist, right? No? The dual basis on Rn star, the dual of Rn, which is possible to identify with Rn itself, by the way. So this is the dual basis. What does it mean? It means that Li Rj, so okay, 1 if I equal to j and 0 else. So this is the ij component of the identity. Okay. Dual basis. So we have now sometimes this is called basis of right. So this basis here actually exercise. This basis that diagonalizes is a basis of eigenvector transposed of A. We know that the transposed go from the dual to the dual. This basis diagonalizes with the remark also maybe. A and its transposed matrix have the same spectrum, have the same eigenvalues. Why is this so? Simply because the determinant of A minus lambda identity is equal to the determinant of A transposed, because this is... Okay, so they have the same eigenvalues, and one checks that this basis here is the basis which diagonalizes, so which means that A transpose of Li is equal to lambda I. Okay. Okay, so this is, of course, when A is symmetric, we don't see the difference between the basis Ri and the basis Lj. Okay? This is a symmetric case. This is not in general. If I have not written anywhere that here A is symmetric, but A has these assumptions here. Okay. Now this is a system of first order of transport equation, linear transport equations, homogeneous. So, and we wonder whether we can generalize what we know. Remember, in one dimension, when capital N is equal 1, we found the solution. Remember, so we want to generalize that formula at least. So here, T and so we are in one space dimension for simplicity. Here, this was true also in n space dimensions. Here we are in one space dimension, but however, this is a vector of n components. Okay. Okay, so now what happens here? Let's consider this system, and then let us multiply this system by Li scalar product ut plus ux equals 0. So, and this is equal to Liut plus, so simply because Li is independent of T, scalar product. Then what I have here, Lia is equal to A transpose Li, A del transpose so this is equal to lambda I U Li Ux. So lambda I U X. Okay. Because if I multiply on the left matrix A by Li, this is equal to multiply on the right with the transposed. Okay? So this is still equal to lambda I Li, and then I put X outside. Okay, so let me call Ui, for simplicity, Ui for any I, Li scalar plot to Ui. So what do I find? I find that Ui satisfies. So essentially, I have diagonalized the system, if you want. So I find that Ui satisfies a linear transport equation. So we have that Ui T plus lambda I Ui X equals 0. Right? Is it no? Is it not clear? It is just this. uyt plus lambda I uyx. No? So we are exactly in the case of the first lecture. Okay. So our system is coupled with some initial condition, this one. Okay, so this gives us qi 0 equal to 0I. If I multiply this by Li on the left. Okay. Well, give 0I if you want is equal to so we know the solution of this. The solution of this is u0I x plus x minus t lambda. The solution of the system. Okay. So check at home. After this, the solutions to 1, 2 is finally even. Right. Okay, if I'm not wrong. It is interesting, this connection with the So please do the exercise at home for the triangle, for the upper triangle. And now I want to, so this is just a remark which connects first order systems with second order, system of PDEs with second order PDE. Now we continue our study of the linear wave equation with some more complicated case, but still in one space dimension. Okay.
Equation for this case, we haven't used the fact that the eigenvalue should be distant one.
Well, I'm diagonalizing each eigenspace is one dimensional. Yes. I use this. In the okay. So let's go on with the equation. Now we want to study the problem of the half-life, because physically we never, in practice, one never study problems in the whole space. One has boundary conditions, bounded domain, etc. No? So in practice, we need to couple with boundary conditions. So let's start to study the wave equation of the half-life. What does it mean? It means that now we have the following problem. So u 1 over c squared utt minus uxx is still homogeneous, but where in, say, positive times, just, but what it is more important here now is on the half line in space. So positive times, because if t is time, we look at solutions in the future, let's say. But now, so we have to give now a initial condition, so that I call u of 0 x, I call it phi of x, ut as before, as yesterday, say, this I call it psi of x, yes, this x larger or equal to 0, see. So, in time space, this is space, this is time, so we are giving, we want to study our solution in this quarter, here, see. We are assigning now an initial condition, initial position, initial velocity on the half line. Okay, but now we have also this as sort of boundary of the domain, so we have to assign also something here. So, and we assign here with the function u of t0, say, equal h of t, this t larger or equal to 0. So now you see we have, this is a Cauchy problem. In the sense that we can interpret this as initial condition, so position, initial velocity. But then there is also a new boundary condition which prescribes u here. Okay? So I'm prescribing u here, and the velocity here. This is related maybe to your yesterday question. This is one possible way to assign boundary conditions. Now let's the assumptions on phi and psi. Okay, phi says C2. We don't want now the problem of distributional solutions, discontinuities, or strange things. So phi is C2, like the solution, because yes, of course, u in C2 okay. So we assume, as I said, so C2, psi C1, H C2, no. And then, however, there should be some compatibility conditions if we want a smooth solution up to the boundary, as it is written here, right? So we want smoothness up to the boundary, so we have to put some compatibility condition between H and phi and psi. Is this clear? So what could be the compatibility conditions? So plus compatibility conditions. Let us try to find conditions between the data of the problem. Psi, phi, and H, phi and psi. Between H. So let's try to see if you're able to imagine which could be the yes. So if I take u at time 0 here, I get h of 0. And if I take u, so h of the first compatibility condition should be this one. This is reasonable compatibility condition. Then, now what happens if I take ut equals 0? This means I am taking ut here, So what do you expect between
H prime of 0 equals to chi of 0.
h prime of 0? We should be psi, right? H prime of 0 should be psi. Yes. But this is not enough. There should be another. So these are conditions on the first derivative, on the function continuity, say C1. But actually, we have declared that we are looking for C2 solution, including this. So, which could be another compatibility condition is on C2 derivative. In your opinion?
The fact to write U is C2 of this product means that U is C2 in an open set?
Yes. Containing. It is one way. Yes. So what happens if I do H second here? So H second, meaning that I am taking UTT here, right? What should be H second, morally? Should be UTT from our PDE. UTT must be equal to C square UXX, but UXX must be this. No? So, do you agree with me that another reasonable condition should be C square phi single? Is it okay? Let me repeat it. So if I differentiate twice here, I get UTT here. I require UTT equals C square UXX. But UXX I differentiate twice here is phi second. Okay, so these are the compatibility conditions that should ensure are important because these are related to the class of regularity where we are looking for our solutions. Okay. Fine, so this is the problem. We want to find the solution to this with this regularity and this compatibility conditions. Now, theorem. Okay, the unique solution is to this. So you can see it, you're imagining, you see when we add the boundary condition, the problem becomes more complicated, but it is at least more realistic. Still it is not realistic, because this is an infinite string, too long. But more realistic than the problem on the wall line, okay? So the unique solution of our problem can be written is, so let me write it, dx okay. And this is not surprising, in some sense, it's the usual formula, but this second one is, so let me copy it, otherwise confusion. So now let me point out some differences. So this is the usual formula, like the formula we found yesterday. Okay, so no, really nothing very new. However, this is a minus here. Okay, and this is exchange sign. Okay. Of course, this is larger or equal than 0. This is larger or equal than 0. And this is larger or equal than 0. As you can see from our constraint here. This is necessary because h of phi and psi okay. Okay, so let's see now how the proof works. Okay. Okay, proof. So if solution exists, it must be of the usual form, the sum of, so if the solution exists, it must be of the form UTX, the superposition of a direct wave and an inverse wave. This is the inverse wave. This is because, remember, the question that you made yesterday, what happens if the domain is strange? If the domain is strange, that formula is not necessarily true. But this domain is complex. So still we can apply our formula superposition of that. So for some alpha, okay. Okay, now we start working using our boundary conditions. Okay, so now we use our boundary initial conditions, try to determine alpha and beta. We use now our initial condition and boundary condition. What does it mean? Let's start doing. So, u at 0x must be equal to phi. Okay, I put time t equals 0 here. And I find the first relation, alpha of x plus beta of x. This must be equal to phi of x. First thing. So I am using now ut. I differentiate, so if I differentiate with respect to t, what do I find? I find c alpha prime, and then I put t equals 0, minus c beta prime of x, this must be equal to psi of x. Okay, second condition. And then also, third condition is what happens if I put x equals 0 there. So if I put x equals 0, I find that third condition is alpha of tc plus beta of minus tc, okay, beta of minus tc, it must be equal to h of t. Okay. Now I leave you as a not difficult exercise to reduce alpha and beta from the first two conditions. Let me write it for you. From this we can reduce alpha and beta. Okay, so alpha of x turns out to be, we can check a posteriori, but I leave you as an exercise. So phi of x plus and beta of x equal 1/2 phi of x minus. Sorry. Let us check that this is correct a posteriori. So if I take the sum of this plus this, the two integral cancels, and I get 1/2 phi plus 1/2 phi, so equal phi, and the first is satisfied. If I integrate, sorry, if I differentiate alpha prime, I take but then I take the difference, so this and this cancel, and then I get 1/2c psi of x divided by 2, minus and minus is plus, and the c is in front of here, and it seems correct. Okay? Okay. So this is just coming from, say, 1 or 3. 3 implies this condition. So now we have to use also 2, 4, say. There is something here. So for tau negative, if I call minus tc equal tau, what do I get? If I call minus tc equal tau, beta is equal to minus alpha of minus tau. Yes, equal. So minus tau, so tau is equal to tau negative minus tc. So this must be equal to h of minus tau over c. Correct? Okay. No, not equal, equal plus. Now, alpha is given there. So alpha is given there is minus 1/2 phi of minus tau minus 1/2c integral from 0 and minus tau psi of xi and xi plus h minus tau over c. And this should conclude, no? Because now it's just and now this concludes the proof. Please check at home that this is consistent with this. No? Because we have alpha, which is there. We have beta, which is here. It's enough to sum, to write now this expression using alpha and beta. So, and the assertion follows. You have to use I, this, 6, and 7. So here you have an expression which is the second one. Here you have another expression which is this one. We have not used the compatibility conditions. The compatibility conditions are necessary to show compatibility conditions ensure if U is smooth enough along this line. Because I'm defining U piecewise. U is something here and something else here. But I have to check that U remains smooth enough along the line. It's not create corners or discontinuities or. And so, and this is where you use the compatibility conditions. Okay. Okay. So this is.
Okay. A question: is it possible without the compatibility condition to have kind of distributional solution?
Yes, in general, yes. But I don't want to, since now the problem becomes a little bit complicated, I don't want to talk about weak solutions. I want strong solutions. Okay. So now let me quickly give you some exercise. So suppose that we fix the string, we keep fixed the string at the origin. This means that we take h equals 0. Okay, so our string here is 0, fixed at the origin. Phi psi are. So, what happens to that expression? So we can write u of dx for times here, say, larger than x. We can write, so h is 0, okay? This means that this is not present anymore, so we can simply write this as minus. So 1/2 phi of x plus ct, 1 half phi of x plus minus, sorry, minus ct minus x. Okay, then we have the integral, 1 over 2c x plus ct. Okay. Then we have minus plus 1 over 2c 0 ct minus x. So we can rewrite this expression in this more symmetric form. So in that region, in this region here, the solution is the sum of a direct wave and another inverse wave. So it's similar inverse, maybe reflected, because this is the reflection, no? So you have the sum of a wave and its reflection, more than inverse in this case. This suggests, so this expression suggests to extend phi and psi by reflection in an odd way. So let me extend phi of x equal minus phi minus x for x negative, psi of x. So I extend phi by reflection also for negative by taking its odd extension. So minus phi minus x. So let me call phi e phi extension of phi, the odd extension. Psi the odd extension. Psi. So I have transformed the problem in this way, and in this way our solution now becomes exactly, if I'm not wrong, as before. In the old way, in the old manner. So the expression is the old one, exactly the old one, when we have extended by disparity, say, phi and psi for negative x. So that expression becomes exactly this, and this is interesting somehow. So check quickly at home that what we have written here. So this is for what concerns the wave equation on the half line. Now let me tell you something more on the finite interval as a last sort of example exercise, which is still more realistic. So all of these things have a physical interpretation in terms of a wave which is reflected back at the origin. But let me skip this physical interpretation and let me go quickly to the case of a bounded interval, maybe more realistic. So let us consider the string on a bounded interval 0, say 0 L. So we want now the more realistic problem, 1 over c squared utt minus uxx equals 0, say u0x equals sigma x, ut0x sin x, as before, and then we have, however, u of t0 equals, say, h1 of t, and u tl equals h2. With h1, h2, now I don't rewrite the assumptions, but smooth enough, okay? Plus the compatibility. So please, home, in order to have a C2 solution, regularity assumption on 5 psi h1 h2, on 5 psi h1 h2, and compatibility conditions. Now we have more compatibility conditions. And between 5 psi h1 h2. Conditions. Now, one way to solve this problem is, again, one way to solve is, again, to go back to the situation number 1, where everything is defined in the whole R. So we extend it by reflection. So phi of x plus phi of minus x equals 0. Psi of x, we extend phi and psi. Phi of x plus phi of phi of x, phi of x, phi of x. So I have extended here negative in an odd way. I want to do the same around L, 2L minus x. Maybe. Okay. Right. Okay. So in this way, we have 12 periodic functions, and we can look for 12 periodic functions, solutions, actually. And there is the constant C. C, period. Velocity. So this is one way, but let me do with more details. So instead of, so we can come back to, so we can write alpha plus beta and look for 12 over C periodic in space solutions. But instead of doing this, insisting on this, I want to show you another way to treat the same problem. Suppose for simplicity maybe, so another approach. Let me suppose that h1 for simplicity equal h2 equal 0. So I have a string which is fixed here and here. And then I let it oscillate, but it is kept fixed at the two boundary points of 0 and 0. Okay. Okay, so what is our problem then? Is this 0? Phi and psi are 2L periodic. Extended by reflection. Reflection with respect to this point and with respect to this point. Now that we have the periodic setting, what comes to your mind when you have the periodic setting for linear PDEs? So since phi and psi are periodic even, odd, sorry, Fourier series. We can expand phi and psi in Fourier series. Let's see what happens. Suppose that phi and psi are sufficiently smooth in order to, I don't know how smooth, but sufficiently smooth in order to have uniform convergence. Maybe phi C2 psi also uniform convergence of the Fourier series. Convergence of Fourier series. Okay, so now we can try to do some expansion. Hoping not to make mistakes. So let us expand in sinus series phi and psi. So phi of x equals some coefficient here that I call an. Okay. An. I hope not to make take 2 over F. Okay. Scalar product phi against the basis sine. Okay. No, because these are 0 and 0. These are even, odd. There is no constant term, usually called A0 over 2, whatever. Okay, and the same for psi. And the coefficient, let me call them Bn. If you recognize this, I think that we have done this in functional analysis, no? This is a basis of the space, Hilbert space of periodic, with two periodic functions on the interval. No? No?
No, in functional analysis.
You have not done anything about Fourier series?
In undergraduate.
In undergrad, okay. What did you do?
So when there is a convergence of Fourier series.
So this say suppose that phi is C2, C1, whatever, in order to have at least uniform convergence of the Fourier series. Phi and psi is sufficiently small. C3.
P and psi must be
Periodic.
periodic and
12 periodic, yes.
it is sufficient piecewise smooth.
Yes, yes. In order to have uniform convergence, I think you have C1 smoothness of the Fourier series. But what is important is that this sinus, this function is odd, therefore there is no cosine terms. It is just written as an expansion of the sinus.
If this function is odd, we can write on the sinus. If it is not, we need to add cosine.
Yes, it is. If you want, it is more convenient using the complex exponential e to the I n pi over L. In the complex notation, maybe it's more clean. No, you have a basis e to the I over e to the I n pi x divided by L, maybe normalized with some constant.
I am saying that we are writing Px only using sinus, yeah?
Yes, because this is odd.
Oh, yeah.
Yes.
If it is not odd?
No, if it is not odd, no. You have to use this sine and cosinus, or if you wish, in complex notation with a complex exponential.
You see then cos.
Yes. And what it is important to realize that
Yeah, given that it's periodic, you can shift from minus over 2 to L over 2 and then.
yes, but what it is important is that it is the two scalar product between one element of the basis and our function. So we have an orthonormal basis of an L2 space in infinite dimension. But you are doing Hilbert spaces, no?
Not yet.
Ah, not yet. You are not.
In the course? In the course of functional analysis?
Yes.
No, we are about to start.
Ah, no.
Hilbert spaces. Not yet.
But you did Banach spaces.
Yeah.
Ah, but you didn't speak you never spoke about basis. What is a complete orthonormal system in a Hilbert space? Ah, okay. I see. Okay, you have to think about that as a sort of generalization, infinite dimension, because we are in, say, in L2 of 2L periodic functions, L2 periodic, and that is a complete separable Hilbert space. We can find always a complete system Hilbert basis, if you want, it is called. Any element can be written as an infinite sum, linear combination, but it is infinite. It is like when you write a vector in finite dimension, when you have a basis, no orthonormal basis, and you write a vector, say, alpha I, ei, no? This is a finite sum, and alpha I is what? Is the scalar product between the vector and ei itself. No? No? Alpha I is b ei. Here we have more or less, it's much more difficult, but we have more or less the same because we are in infinite dimension, but one can prove that that is a basis. No, sine and cosinus is a basis. So this is a basis, actually. Okay. There is also the constant here, also for n equals 0. It's a basis. Basis means that well, basis is not so easy to define, but it is the analog of a basis. It is orthonormal. So if you take, for which scalar product is there to scalar product? No? So in this case, it is a scalar product, say f of x divided by x. And therefore, this is nothing in real notation is nothing but the scalar product of our vector phi and the nth element of the basis. That's it. So it is exactly this an takes the role of this alpha. Of course, there is a lot of things to prove, series convergence, but okay. Okay, so now okay, so we have, once we expand, once we have extended everything by periodicity and by reflection in this way, we have, as I said, our usual expression, phi of x plus tc plus phi of x minus tc plus 1 over 2c. And then we have to expand this in Fourier series. Psi of psi. So what do we have? So we have to be very careful here. So we have 1/2 sum and larger or equal than 1. An sinus pi n x plus tc sinus pi n x minus tc. Okay. And this is what it is written here. And then we have 1 over 2c bn sinus pi x. Okay. Now the convergence of the series is so strong because of our regularity assumption of psi, see, that this integral sum can be interchanged. Okay, so let's try to compute separately this. So this we can do. So what is this? Think what happens here? Cosinus, so there is a minus here. Then I think there is here there is an n, and here there is a pi, and there is 1 over n. It's correct? Oh. So let's forget, okay, this 1 over 2c maybe, okay, So let's omit 1 over 2c. I just compute the integral, okay? So then I will multiply them. So for simplicity, let's forget about this. So what is important here is, so we have the n, then there is, as I said, L over pi, there is a minus, there is an n here, right? And then cosinus of pi n x plus bc minus. Correct? There is some C missing, I'm sorry. I missed C everywhere. No, I cancel. So, at the end, when I do 1 over 2C, let me check if I... So this is 1 over 2C, and so this is 2C pi. And it is very important, the presence of this new n here at the middle. So, this is, so in this way, once you substitute this here, you have a representation of your solution. A little bit more explicit than, no? So your solution can be represented as this one plus this one. Okay? So I leave you as an exercise to find another representation of the solution, home, so that you start to work a little bit. It's important to work with Fourier analysis. Fourier analysis is a fundamental part because it's very clever to find the simplest basis of these infinite dimensional spaces is very important in general. Finding new basis or useful basis. You can imagine, you know how important even in finite dimension to have a good basis to make computation. And here is the same. In infinite dimension. So the home exercise is the following. Home. Another representation. Equivalent to represent the solution. So is UTX, if I'm not wrong, is sum an cosinus n pi CTFL plus dn sinus so still in the basis signs. This is the basis before. So an and bn are the same as before. The same as before. Please check this if this is correct or not. 5 sine 5 So Okay, try to do the computation. It simply should follow simply by the previous expression, expanding cosine alpha plus beta equal cosine alpha sinus beta minus sin alpha, arranging terms. Should be simply that one. Okay, so now the last comment I want to tell you on this. So this concludes, if you want, our short trip into the one-dimensional wave equation. But let me tell you a general result, which is at least easy to state for the wave equation. So what about uniqueness? So now we pass to the n-dimensional case. Okay. Okay. So suppose that omega is inside Rn, bounded, open, connected, open, connected, and take a positive time, and consider the following, and consider a solution, consider the following problem. So I put c equal 1 here just for simplicity. So UTT minus Laplacian of u equal f in omega. Now we comment on that. U equal h. And UC2, say. Suppose that F and G and H are sufficiently smooth. Sufficiently smooth. And U is a solution of class C2. Then if a solution of one exists, it is unique. The statement is the following. Then if a solution exists, so we don't pretend to prove existence but we of a smooth solution like that, but we pretend to say that if a solution exists. So let's see what is the situation. We have omega here. Some positive time. Then we are considering an object like this. So 0 t times omega. 0 t times omega. We assign boundary conditions, so when we close this set in the whole time space, the closure is of course this one. Okay? Closure is of course this one. So when I assign u equal g in the closure minus the sets, it means that I'm assigning u equal g essentially here. Minus, well, but u is equal to a, so u equal g here, and u equal h here. So I'm assigning 0 t minus 0 t. Maybe here there is maybe here there is a parameter. So here u is equal to h at time 0, here is u is equal to g. Okay? Now if a solution exists, it is unique. This is the result. Let's see if I'm taking the correct boundary conditions. Because we define for any t, say in, okay, suppose that you have two solutions, u1 and u2, and define w is the difference, u1 minus u2. You want to show that w is 0. Okay? Need to show okay. What is the solution? What w solves? Everything is linear here. Okay. So we just have this, and then we have w equals 0 everywhere on the bottom. Okay? Because I take g minus g 0, h minus h 0, f minus f 0, the difference of this is WPT, so w is 0. This solves this. Now I don't rewrite where, but it's clear, no? Okay, now I introduce the following quantity. So let me call it ET. This is called the energy method. So this is WT squared plus gravity squared dx for any t sin 0t. So I take the time slice here, okay, and on this time slice I'm integrating. So what does it mean, this expression? More precisely, it is this. And so t dot square plus gravity t dot square. Okay, is it clear what is this? So I'm integrating on this time slice the energy of W. This is the number to the square, this is the gradient square. And then I look for an ordinary differential equation satisfied by E of t. Okay, so I leave you to check. Then here you have to use the Gauss-Green theorem and the boundary conditions, but I leave you to check that this is omega t I leave you to check this. But if this is true, then this must be 0 because WT verifies the PDE. So hence equals 0. So the point is to check this sequence. And to do that, you have to use, I think that this kind of computation can be found exactly the same in the book of Evans. Evans partial differential equation. exactly as it is. So this means that ET is constant. If this is true, ET is constant. Okay? Now there is, how do you conclude?
It is 0.
That's here.
Huh?
It's
So-
not here.
ET must be equal to E0. But why E0 is 0? Yes, by the boundary conditions. Exactly. Okay. So please check the details in this proof. Details here, and the details this Gaussian theorem. Here you use the PDE, and here you use the boundary conditions. Nothing is said about existence here. I don't say anything about existence. Just say uniqueness of a solution. Okay, so this concludes what I wanted to say for this beginning of the course on the wave equation. And the next time we will pass to some other type of equation.